Welcome to Lesson 5E, runge+kutta technique. In this lesson we'll explain the runge+kutta marching technique, how it uses weighted average slopes, and I'll do some examples of runge+kutta in both Excel and MATLAB. Here's a summary of how the technique works. There are 4 steps. Starting at Tn with known function Fn, we calculate the slope there, call that d1, and we extrapolate to point 2 at the halfway point Tn plus a half, using that slope d1. This is our first intermediate step. Step 2, we calculate d2 at point 2, that's the slope here, d2, and we extrapolate f to point 3 using that slope d2, keeping our color coding. This green line represents extrapolating to point 3. Step 3, we calculate d3 at point 3, that's this slope d3, and then we extrapolate to point 4 using that slope, which I colored in purple. This point 4 is now at Tn plus 1. Finally, we calculate d4 at point 4, that would be this slope here, and we extrapolate f to its final value using this slope. But this slope is not d4. Instead, it's a weighted average slope made up of all 4 of these intermediate slopes. So fn plus 1 is fn plus delta t times this average slope, which is represented by this red dashed line that goes all the way up to Tn plus 1. This is our final predicted value of fn plus 1. As I comment here, notice that the 2 outer slopes are weighted less important than the 2 inner slopes, d1 and d4 being the outer slopes, and d2 and d3 being the inner slopes. You can see that this runge+kutta technique is a kind of predictor-corrector technique, except with 4 separate steps and a weighted average of 4 slopes. Some comments. Runge+kutta is explicit. No iteration is required. Unlike the backward difference technique or the central difference technique, here we have no need to solve for dn plus 1 implicitly. The explicit nature of the runge+kutta technique makes it very attractive. The runge+kutta technique is actually 4th order accurate. It's also very stable, but it's not unconditionally stable. At large enough values of delta t, it can still go unstable. Runge+kutta can be used for any number of first-order ODEs, even nonlinear ODEs. All you need are equations for the derivatives of each variable. Then you can solve or march in time with the runge+kutta technique for all the variables simultaneously, given some initial conditions. I programmed runge+kutta into Excel, and I do a simple example for one variable, f as a function of time, given by this equation. I'll show this live in Excel, where we'll see this plot as our result, where I compare all of the techniques we've discussed, along with the exact analytical solution. This is for one particular time step, but I'll vary the time step in the live demo to illustrate the behavior and accuracy of each scheme. I'll now show this live in Microsoft Excel. Here's my Excel spreadsheet. The cells in yellow are what I enter: starting time, a delta t, the initial value of f, 7.6 as you can see here, constant a and constant b from this equation, and I picked this simple equation that has an analytical solution, which I plot in red. You can see it's just an exponentially decaying function. Then I used 5 different time marching schemes, the 5 that we've discussed. I also color-coded everything, so I made columns of time, coefficients a and b, which are constants in this example, but I set it up so that they can actually be functions of time. Here's the exact solution: forward difference, backward difference, central difference, predictor-corrector, and finally runge+kutta. Notice all the intermediate steps. I plot all of them on this plot. Compared to the exact, the forward difference underpredicts, the backward difference overpredicts, the central difference is in between the two, the predictor-corrector does very well, and the runge+kutta does extremely well. If I make delta t very small, for example 0.002 seconds, all of them do very well. Let's keep increasing the time step. 0.005, I'm starting to see some deviation from the exact. 0.01, more deviation, especially from the backward difference. 0.02, more noticeable differences. 0.05, which is what I started with. 0.1, Notice that I did not use the smoothing function, so these kinks are actual data points. every 0.1 seconds is a new data point. The first order forward and backward schemes are very far off. Central difference is second order, and it does a reasonable job. Both the predictor-corrector and the runge+kutta do well. You can notice some small differences in the predictor-corrector scheme at this location. 0.2, now we see much bigger errors. Even the predictor-corrector is not doing all that great, but the runge+kutta is almost right on.
Sir, the runge+kutta technique seems to be perfect. Does it ever give wrong answers?
Well, it's not perfect, BJ. The values it gives are not exact. We can see that if we make delta t even larger. Let's try 0.4. With such a huge time step, none of them except the runge+kutta do anywhere near the analytical solution. And even the runge+kutta is showing some deviation from the analytical solution. I did the same example using MATLAB for the same equation and same variable. Here's a copy of the MATLAB code. MATLAB has a built-in runge+kutta type scheme called ODE45. This subroutine needs derivatives, a time span, and the initial values of f. Here f is just one variable with the same initial value I started with, and t-span is from 0 to 1, as in the Excel example. We have our plotting functions and printing functions. The only other thing we need is a function for the derivatives. Here we need just one. I called it df dt. Here are my constants a and b, and df dt is b minus af, which is the equation we're solving. When you run MATLAB with this code, it generates the exponentially decaying curve for f as a function of time. This curve matches the exact solution nearly identically. Here's another example MATLAB code where I solve for two variables simultaneously. I'm looking at the motion of an object that's moving in time in the xy plane. Now I have two variables which I call position 1 and position 2 along with the time span. The syntax is the same with ODE45 where we have the derivatives, the time span, and now both variables in a 2x1 array. These are the initial conditions which I specified here. Again, we plot this time with equal axes, and the function for the derivatives is what I called RK_derivatives. First I created an empty column vector and then filled it with these derivatives. In this case, df dt for the first variable is its position 1, and df dt for the second variable is given by this equation that I made up. Notice that it's nonlinear. When we run, we see the trajectory or the path of this object with time, where we're plotting y versus x. So we predict the path of the object. This is what we have been gearing up to do for the past several lessons. Namely, we can extend this to any number of variables, which are x and y for each vortex, and then we can predict the mutual interaction of many vortices. I'll illustrate with two vortices. Recall the equations for the derivatives of our four variables. For two vortices, we have four variables, x1, y1, x2, and y2, which are the spatial coordinates for the two vortices. These are our functions of time. We have four ordinary differential equations, which we developed in lesson 05C. These are expressions for dx1 dt, dy1 dt, dx2 dt, and dy2 dt. I show a screenshot from lesson 5C below. In MATLAB, our position variable is actually a column matrix of the four variables with initial conditions specified, namely the initial positions of the two vortices. Our derivatives are functions of time and position, also a single column vector with four elements, dx1 dt, dy1 dt, dx2 dt, and dy2 dt. I won't show this because I always make my students do this for homework, but I'll go back to the previous example. You have to add two more lines here for DFT 3 and 4 and change the right-hand sides appropriately. Of course, some other numbers need to be changed, along with all the initial conditions and the values of gamma for each vortex. We march in time using the runge+kutta technique, which in MATLAB is the ODE45 function. I'll show the results for an example, namely the rotating vortex pair of lesson 05C. This consists of two identical vortices starting at two different locations. One vortex started here with circulation gamma and the other vortex started here with the same circulation gamma, namely at 1 and -1 along the x-axis. By mutual interaction, this vortex causes this vortex to move in a circular trajectory, and runge+kutta accurately predicts this trajectory all the way to the other side. I set my time span, knowing this speed and covering this half circle to stop exactly at this vortex. Similarly, this vortex has an induced velocity from the other vortex that is again counterclockwise, and it moves along this blue path all the way to the other vortex. This solution agrees nearly identically with the analytical solution of circular orbiting vortices. Again, I illustrate this just for 2 vortices, but you can easily extend this to any number of vortices. Each vortex will have 2 variables, x and y. So writing the code in MATLAB can get a little tedious, but it's not much more difficult than what we've done here with 2 vortices. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.